Hello everyone, Science Spot is a podcast that shines a spotlight on the latest scientific technology from Japan. Your host is Ren from Science Talk. Today I'm going to talk about a discovery by a joint research team from Hokkaido University and Toyama University. This research provides a theoretical answer to a long-standing challenge in material science, creating tough materials that possess both strength and resistance to breakage. First, what comes to mind when you hear tough material? For example, our bones or diamonds are prime examples of tough materials that are not only hard but also don't easily break even under some impact. On the other hand, some like glass, though hard, can shatter instantly with a small impact. We call this brittle. In the field of material science, achieving both hardness and toughness has been one of the most difficult challenges. This is because generally making a material harder tends to make it a bit more susceptible to cracks and thus brittle. To give you an analogy, imagine a crispy cookie. It's delicious, but it crumbles easily with a little force, right? That's brittle. In contrast, a chewy caramel is soft, but it's hard to tear apart. That's a ductile material. The ideal materials would have the hardness of the cookie, but the chewiness and the resistance to breaking over caramel. Through past experience and their analysis of tough natural materials like bone and diamond, it was empirically known that mixing soft and hard materials could be effective in creating tough substances. However, fundamental questions remained unanswered. Why does mixing them make them tough? What ratio should they be mixed at to achieve maximum toughness? It was like trying to bake a perfect cookie without knowing the optimal recipe. This time, researchers took on this long-standing mystery. They constructed a linear elastic body model where soft and hard elastic elements are randomly mixed. This is a simplified, abstract, or virtual material model that represents real substances. This model only requires setting three important variables, and it's like defining the type of ingredients and their ratios in cooking recipe. Elastic modules ratio of soft to hard elements. This ratio tells us how much stiffer the hard material is compared to the soft material. Second, ultimate elastic energy density ratio of soft to hard elements. This ratio indicates how much energy each materials can absorb before breaking, representing their toughness or resilience. Third, volume fraction of soft elements. This is the mixing ratio showing what percentage of the total composite materials is made up on the soft material. The research team systematically explored the various combinations of these three variables using large-scale computer simulations. This is like trying our tens of thousands of materials recipes in a virtual space to comprehensively investigate how each materials would fracture. And from these simulations, the results are revealed. First, they discovered that the fracture behavior of mixed materials changes significantly depending on the mixing ratio of soft and hard elements. When the proportion of hard elastic elements is high, brittle fracture occurs, meaning the materials break suddenly, like glass shattering. Conversely, as the proportion of soft elastic elements increases, Ductile fracture occurs where the materials deform significantly before breaking, much like a plastic bag tearing. They found a critical volume fraction of soft elements, where this transition from brittle to ductile fracture happens. This critical point is determined by the material properties ratios of both elastic elements. This is a crucial indicator for predicting a material's fracture characteristics. Even more importantly, in the region where ductile fracture dominates, they found that there exists an optimal volume fraction of soft elements that makes the mixed material most tough. Unremarkably, this optimal mixing ratio for maximum toughness was found to depend only on the ultimate elastic energy density ratio of soft to hard elements, or the resilience ratio. This discovery provides an incredibly simple yet powerful guideline for material design. Until now, creating tough materials often relied on researchers' experience and their intuition. But with this new research, we now have theoretical guidelines that tell us what properties materials should have and at what ratio they should be mixed to create the toughest possible material. This has the potential to dramatically simplify the material development process. This achievement is expected to significantly contribute to the development of tough artificial cartilage in regenerative medicine, as well as diverse materials like rubber and ceramic, which are even used in the aerospace applications. And our future products may become safer and higher performing thanks to this new recipe. That's all for today's Science Spot. This podcast is broadcast daily on weekday morning in both Japanese and English. I hope today's discovery has changed how you view the materials around you. I'd love for you to listen to the podcast and post your notes and thoughts with the hashtag Science Spot. See you next time.